Hi everyone, Physics 30 Unit 3, Electromagnetic Radiation, or EMR. Section 1 is EMR as a wave, Chapter 13. So there's a bunch of curriculum outcomes I'd like for you to review. I won't read them all, but go ahead and look at them at your leisure. Basically, we're going to abbreviate electromagnetic radiation as EMR. Okay, there is a wave model and a particle model. The particle model is Chapter 14. Okay, so we're going to describe how accelerating charges produce EMR. Okay, we're going to figure out how EMR reflects and refracts, goes through different interfaces. We're going to talk about something called diffraction. We're going to talk about Young's double slit experiment that supports the wave model of light. We have a whole bunch of formulas for that, a whole bunch of formulas for refraction of EMR and light. We're going to calculate the speed of that. So there's just a few of the things we're going to do. Okay. So the checklist of things that we're going to do for this section. Okay, so there's a pre-assessment and then 5 parts to this. So what is EMR? The speed of EMR, reflection, refraction, and diffraction and interference. Okay, so there'll be notes, examples, and practice problems for each of those. Okay, of course, at the end, like the other units, there's going to be a formative assessment, which is not for marks, a curriculum review, which is for marks, and then, of course, a quiz. As this unit is another 2-section unit, chapters 13 and 14, there will be an exam written at the end of section 2. Awesome, so let's get started. Part 1, what is EMR? Because Faraday believed in the unity of nature, he speculated that there was a relationship between light, electricity, and magnetism. Faraday was encouraged by this idea when he demonstrated that light traveling through heavy glass had its plane of polarization, basically how the waves went up and down. Okay, the plane of polarization was rotated by a magnetic field applied to the glass. Faraday, however, lacked the mathematical skills to prove that these light waves could travel by electric and magnetic fields. Okay, so introduce Maxwell. Okay, Maxwell, in the 1860s, developed a theory to mathematically express Faraday's speculation. Okay, so he kind of took Faraday's ideas and said, hey, I think I can do the math for this. Okay, this theory is known as the theory of electromagnetic radiation. This model will be examined without going into the mathematics because they're not only beyond the scope of our course, they're beyond, way beyond the scope of this course. So anyways, moving on. Okay, the 4 guiding principles of Maxwell's theory. Okay, remember last year we talked about Ørsted, and we also talked about Faraday a little bit. Okay, and they established the 2 basic principles of electromagnetism. Ørsted, remember, he said the electric current will produce a magnetic field. This was the motor effect. And then Faraday countered, saying a magnetic field can be used to produce an electric current. That was the generator effect. So Maxwell added to and generalized these principles so that they apply to electric and magnetic fields in conductors, insulators, and even in free space. Maxwell's principles of electromagnetism are then stated as: a changing electric field in space produces a magnetic field. The magnitude of this magnetic field is proportional to the rate at which the electric field changes. Okay, so the magnetic field, remember the symbol is B, that little, it's an infinity sign that just doesn't have the end drawn in. Okay, that's proportional. So the magnetic field is proportional to, remember, delta, that's changing, okay, or change in. So the E with the bars is electric field. So the magnetic field is proportional to a changing electric field over time. Okay? So the second one, then, is a changing magnetic field in space produces an electric field. The magnitude of this electric field is proportional to the rate at which the magnetic field changes. Well, wait a second. If a changing electric field makes a magnetic field, and a changing electric field makes a magnetic field, and vice versa, right? I think I said that proper. Okay, then they're going to work together, right? Right. Well, remember, this is called electromagnetism, electricity and magnetism. So, okay. So to explain the last two principles, Maxwell used the concept of a displacement current. Okay, kind of a new idea. So imagine an atom or a molecule suspended between two parallel plates. So two parallel plates, and here's a little atom. And remember, those atoms are surrounded by electrons. And we'll just draw those in. You can remember the Bohr diagrams from years ago in chemistry and Science 10. All right, if these plates are connected to a battery, okay, so that the top plate becomes positive and the bottom plate becomes negative, okay, the electrons will be displaced to the top of the atom, right? The electrons are going to be attracted to the top plate. Now, we're not talking enough current to actually strip the atoms off of the electron. We're just talking enough to make them move to the top of the electron orbit, okay? Now, the electrons then will be displaced to the top. In order to obtain this displacement, there had to be a movement of electrons, right? The electrons had to move. Well, as soon as you guys move electrons, that's called a current, okay? And in this case, it's called a displacement current because the electrons basically just move, okay, from the bottom to the top, and it's not a very big distance. The movement does not last for very long. So in order to maintain it, the charges on the plate can be increased, decreased, or even reversed. This can be done by constantly changing the voltage between the two plates. If the voltage changes, this is the important part, if the voltage changes, the electric field changes. So look, if I change the voltage between these two plates, the electrons are going to go back and forth and up and down, okay, and of course every time they do that, okay, they're doing that in response to a changing electric field. Well, remember, a changing electric field makes a magnetic field, okay? Well, and as the electrons move, well, we'll get into that part as well. As they move back and forth, their velocity changes, right? And, well, of course, by QVB, right? Fm equals QVB. Okay, if the velocity changes and the force is the same, then the magnetic field will change as well. So, hey, we're setting up this changing electric field to make a changing magnetic field. All right, bear with me. I know there's a lot of theory going on. Okay, it can be said, therefore, that a changing electric field will result in a displacement current, moving charged particles, which, of course, you guys know from last unit, produces a magnetic field. If a changing electric field produces a magnetic field, then scientists, believing in the unity of nature, believe that a changing magnetic field produces an electric field. Of course, that's Maxwell's fourth principle. Maxwell assumed that this model, developed for matter, applies to free space, and this may seem like a big assumption, okay, but it's what Maxwell's theory is based on. Okay, according to this theory, a changing magnetic field will produce a changing electric field, and changing electric field will produce a changing magnetic field. Okay, and once this process is started, it sets up an unending sequence of events. If a charged particle is accelerating, the magnetic field is changing. The magnetic field around a current-carrying conductor depends on the rate of flow. For a steady, constant current, the magnetic field is constant. If the current changes, so does the magnetic field. Therefore, an accelerating charged particle will produce a changing magnetic field. According to Maxwell's theory, this will set up the unending sequence of events. Okay, well, this unending sequence of events is what Maxwell called the electromagnetic wave. Okay, it is made up of vibrating electric and magnetic fields that constantly regenerate each other. At any point along the wave, the electric field is perpendicular to the magnetic field. Okay, so in this little picture, so you've got an electric field moving up and down. Okay, so it goes up and down. Okay, and as the electric field changes, so does the magnetic field, and the magnetic field kind of goes in and out of the page. So at the very end of this video, I stripped a video off of YouTube that shows that the generation or the propagation of this wave very, very well. So just in case you can't make heads or tails of this picture, okay, there's an animation coming at the end. So awesome. Okay, an accelerating charged particle is required to initiate this electromagnetic wave. Maxwell calculated the speed of propagation, okay, the rate at which the magnetic field produces the electric field and vice versa. Okay, so he calculated the speed to be 3.0 times 10 to the 8th meters per second. Now, he did this just a few years after Foucault measured the speed of light to be 3.0 times 10 to the 8th meters per second. Hey, wait a second. So from that calculation, Maxwell concluded that light has to be a form of electromagnetic radiation, just as Faraday had speculated. Maxwell had developed the theory that brought together light, electricity, and magnetism. Okay? Maxwell predicted that electromagnetic waves of many different frequencies could exist. All such waves would travel through space at the speed of light and would have the same properties as light. That is, they would reflect, refract, diffract, interfere, and could be polarized. And we're going to talk about all of those things in the coming lessons. Awesome. So let's talk about Heinrich Hertz. Okay, in 1886, Hertz succeeded in producing and detecting these electromagnetic waves. Remember, Maxwell never actually produced or detected these waves. Maxwell only predicted they existed. Okay? Using a spark gap across which electric charges or electrons could move rapidly back and forth, okay, Hertz generated electromagnetic waves whose frequency was in the 10 to the 9th hertz. Okay, now remember, 10 to the 9th is about a billion. So a billion hertz or a billion cycles per second. Okay, he detected these waves some distance away using a loop of wire as the receiver or an antenna. Hertz was able to show that these waves traveled at a speed of 3.0 times 10 to the 8th meters per second and that they have the characteristics of light waves. That is, they could reflect, refract, diffract, interfere, and polarize. Okay, Hertz called these radio waves. Hertz's discovery of EMR, of radio waves, was taken up by Marconi probably. Okay, sorry about that. Okay, who was the first to transmit radio waves across the Atlantic Ocean in 1901. Okay, this is a huge technology, right? Because these are radio waves, and if you can transmit radio waves across the Atlantic Ocean, now you don't have to wait 3 months for a letter from one side to the other, and communication over long distances finally became possible. So let's talk a little bit about Hertz's apparatus. Hertz's apparatus was basically a step-up transformer using direct current in combination with a switch in the primary coil and a spark gap in the secondary coil. Guys, please don't worry too much about the specifics of this. You'll never get tested on just this thing. It's just kind of interesting, and you need to know a little bit of the background on how these things came about. So don't panic. There's not a lot of questions on this, so just, it's okay. Okay, these accelerating electrons produced an electromagnetic wave which is detected by a receiver some distance away. So basically, when this apparatus was going, there would be electrons moving across this spark gap back and forth. Okay, and of course the moving electrons made the changing electric field, changing magnetic field, okay, that went and then was detected over here at the antenna. Okay, very cool. Now, of course, the more powerful you make these coils, the further this wave can be, or the stronger that wave can be, so the receiver can receive those waves at a greater distance. Okay, moving on. Okay, so let's talk now about the electromagnetic spectrum. Okay, so there is a broad range of continuous frequencies for electromagnetic radiation called the electromagnetic spectrum. Electromagnetic radiation, or just EMR, may also be described in terms of wavelength and energy as well as frequency. It should be noted that frequency, wavelength, and energy are all mathematically related. Okay, so here are two diagrams of the EMR spectrum. Okay, we know this part. Very well. This is the part of the EMR spectrum that we can see. This is light. And light goes from violet and transitions to blue, green, yellow, orange, and then to red. Okay, we know this better going the other way as Roy G. Biv, the colors of the rainbow. Okay, kind of neat. Now, here's the idea. So this one's a little bit backwards from Roy G. Biv. It's BV, whatever. Okay, you get the idea. Now, some trends you need to know about the electromagnetic spectrum. Okay, at the low end, violet has shorter wavelengths than red. Okay, so you can see here, okay, up in this part of the spectrum, okay, has really short wavelengths. The far part of the spectrum has really long wavelengths. Okay, the shorter the wavelength, the more energy we have. The longer the wavelength, the less energy we have. Okay, so violet has more energy than red light. Now, if you have a look, there's all these other parts of the EMR spectrum. So the highest ones are gamma rays, okay, then X-rays, then ultraviolet, okay, then we have our visible light, okay, and then so ultraviolet bleeds into just violet, right, and then we go down to red light, and then we have infrared. So remember, infrared is kind of like heat. It also is the wavelengths that our remote controls use, like for our TVs and whatnot. Okay, and then we have, after infrared, is these radio waves. So there's radio waves are kind of branched out into different categories. They're responsible for radar, TV waves, FM and AM radio. Okay, so just because they're called radio waves, they do other things. Okay, anyways, so that's that. So big things. Shorter wavelengths means more energy. Longer wavelengths means less energy. Now, longer wavelengths, of course, too, these ones have less frequency. Less frequency. And these ones, if you have a shorter wavelength, that's a higher frequency. Higher frequency. Okay, so here's another view of the EMR spectrum. Okay, so again, so this time we're starting at the longer wavelengths, okay, on the left. So we have long waves, and then of course we have the radio and TV again. Okay, microwaves is shown in the middle of this one. So microwaves are between radio and infrared. Okay, and yes, it is microwaves that are responsible for a microwave oven. Yes, so that heats up our food. Okay, that's kind of cool. Okay, then we have infrared again, then visible, so then Roy G. Biv. Okay, visible light is about 750 nanometers up to 400 nanometers. Okay, nano, remember, is 10 to the negative 9. So it's 750 times 10 to the negative 9 meters. Well, remember, that's not really scientific notation. So if we move the decimal place 2, so that's 7.50 times 10 to the negative 7 meters. So that's kind of the far end of what our eyes can see. And then, of course, 400 is 4.00 times 10 to the negative 7 meters. Okay, so that is the extreme high end of what our eyes can see. Okay, moving past or shorter than 4.00 times 10 to the negative 7. Okay, that gets into ultraviolet light. Okay, and ultraviolet bleeds into X-rays, then into gamma rays. Okay, so that's just some basic trends. Okay, now from the electromagnetic spectrum, notice that visible light is a very small part of it. Visible light has that range, 4.0 times 10 to the negative 7 meters to 7.5 times 10 to the negative 7 meters. Okay, now recall the universal wave equation that you learned in Physics 20. Okay, so V equals F lambda. Remember, lambda is that upside down Y kind of thing, so draw it like this. Okay, now V, of course, is the speed of the wave. Lambda is the wavelength, always measured in meters, and F was the frequency, always measured in hertz. Okay, the speed of EMR, okay, remember, it's all C, it's all the speed of light, okay, which is 3.00 times 10 to the 8th. That is on your formula sheet, by the way. Okay, The greater the frequency of EMR, the greater its energy. So high frequency, again, means high energy. So that's those really short waves. That's high energy. The really long radio waves, that's low energy. So low energy. This one's high energy. This one is a high frequency. Remember, frequency means how often it happens. This one's a low frequency. Okay, and this one is a very long wavelength. The energetic ones have very short wavelengths. Okay, again, just patterns. So, reading down here now. All EMR is produced by accelerating charged particles. Radio waves, including television signals, and microwaves, so radar, are produced by the oscillations of electric current. Infrared radiation is produced by molecular vibrations. Visible light and ultraviolet are produced by transmissions of electrons and atoms. X-rays are produced by high-energy electrons undergoing rapid deceleration by hitting a target, and gamma rays are produced by the decaying nuclei of unstable atoms. Okay, so now we're going to talk very briefly about each individual kind. Okay, so radio waves. Radio waves are mainly used in communication, so radio, TV, and some cell phones use radio waves. So microwaves are extremely high frequency radio waves. Okay, microwave ovens produce wavelengths of around 12 centimeters. Okay, microwave ovens operate at a frequency 2.45 times 10 to the 9th hertz. This frequency causes water molecules to vibrate, and you'll remember that since temperature is just the measurement of the average kinetic energy within a substance, the more the molecules vibrate, the more energy they have, and this is noted by us as an increase in temperature. Okay, so radar signals are high-frequency microwaves. Radar was developed to detect objects and determine their position. Radar is simply an acronym meaning radio detection and ranging. Okay, some cell phones use microwaves, as does satellite communication. Okay, so that's kind of neat. Infrared. Remember, infrared radiation is associated with heat. The hotter the object, the greater the infrared radiation coming from that object. Okay? The uses for infrared, so remote controls, heat lamps, alarm systems, and infrared cameras. Okay? So visible light, of course, that's from wavelengths 4.0 times 10 to the negative 7 to 7.0 or 7.5 times 10 to the negative 7 meters. Negative 7 meters. Wow, that's terrible. Negative 7. Okay, I should just, do that properly. Negative 7 meters. Okay, the spectrum, of course, is Roy G. Biv. Okay, really, the book that I took this from, it doesn't have indigo in there because you can't really distinguish indigo from the blue and the violet, but it is there because it's Roy G. Biv. Okay, not Bov. But anyways, whatever. Don't worry about it. Okay, ultraviolet. Okay, ultra, of course, means beyond. So ultraviolet means beyond violet. The wavelengths are 4.0 times 10 to the negative 7 down to 0.1 times 10 to the negative 7. So remember, we're getting shorter. Okay, now these, remember, the shorter the wavelengths, the more energy they have. So this energy, okay, when it hits our skin, it can cause sunburn. Okay, in really bad cases, it can cause skin cancer. Okay, now some UV is blocked by the ozone layer in our atmosphere, which is why there's so much conversation about our ozone depletion, because if we don't have an ozone layer, then a lot more ultraviolet light gets through, and yeah, we get a lot more sunburns and skin cancer and worse. Okay, so X-rays are next, and they're used in medicine, of course, to take pictures of your bones, and in airport security. If you get too much of these can cause cell damage, very bad. Okay, that's why they always cover you in the dentist office with a lead vest when they want to take an X-ray of your teeth. Okay, the lead, of course, blocks the X-rays. Okay, then lastly that we're going to talk about is gamma radiation. Okay, and that's produced by the nuclei of unstable atoms. Okay, it carries the most energy of all EMR, therefore it causes the most damage, so it's the most dangerous. Okay, it's high energy that can cause cancer, but gamma radiation is also used in medicine to destroy cancer cells. It's kind of a neat little twist. So if you can direct the gamma rays at the tumor, it will actually kill the tumor without damaging, or at least too much, the cells around it. So that's kind of cool. For those of you who know comic book lore and the theory behind the Incredible Hulk, remember Bruce Banner irradiated himself with gamma radiation, okay? And the result is he became the Incredible Hulk. His cells mutated and stuff. And it's kind of crazy. So anyways, if you're interested in more of that, you can look that up on YouTube. And all sorts of fun. Now, I alluded to this video a little bit earlier. So this one is the one with the changing electric and magnetic fields to make the light wave. So at the end of this, I'm going to clip that video, just tack it on to the end so you can see it. So just keep watching. Okay, and after you finish that, I want you guys to practice this stuff. It's basically general information, okay, but it's section 13.1 in your textbook. What is EMR? So page 647, numbers 4, 5, and then 7 through 12. So some basics on this stuff. Feel free to read the textbook too, because there's a lot of theory in this section. So anyways, enjoy the little clip that's coming next, and I will see you next section. Thanks. Hi everybody. Okay, funny story. We love technology, but it doesn't always work the way we intend to. It was my intention to link this video right at the end of the current one, and when I tried to do that, it didn't quite work, so sorry about that. So what you'll have to do is you'll have to go to the workspace, get the electronic copy of these notes, and then just click on that link right there. And it'll take you to the website, and then you can watch it just live. So sorry I could not make it work just from just putting it on the video. So you guys will just have to do that yourselves. It's a really good animation of the electric field going vertically, and then the magnetic field coming in and out. Wow, that's a terrible drawing. But you get the idea. So please check out that link. And sorry I couldn't link it for you, but that's just the way the tech works sometimes. So thanks everyone. See you next section.